This question asked you to predict the products and draw the mechanism for this reaction. This is a substitution reaction, so the first thing to do would be to figure out whether the mechanism for this particular substitution would be the SN1 or SN2 mechanism. If we find the leaving group on the electrophile, one thing that we notice is that it's not a very good leaving group because this would leave as OH-, which is a strong base, whereas weaker bases tend to be better leaving groups. But this is the best leaving group option that we have on the electrophile. So if we look at the carbon next door, that would be our reactive carbon, and it's bonded to 1, 2, 3 other carbon atoms, meaning that this is a tertiary electrophile. Tertiary electrophiles can only undergo SN1 reactions, and so this must undergo an SN1 mechanism. Now, addressing the fact that we have a poor nucleophile here, this is going to be helped by the fact that we see that in this reaction there's a catalyst that's added, which is this HOHCH3. So we've got essentially what this is our nucleophile, which is on the top, except it also has an extra hydrogen and a positive charge on it, so an extra H+ with it. This catalyst is going to do our first protonation step, which is going to be an acid-base step that happens before the substitution reaction, which will help make a better leaving group. So in our first step, what we're going to do is that protonation step to make a better leaving group. We will use the acid catalyst, so the electrons go from the leaving group to the hydrogen, and then the bond breaks, giving the electrons back to oxygen. This is essentially making more of our nucleophile, the methanol. Now, the reason that we used the acid catalyst rather than the nucleophile to do the protonation step here is because it is the stronger acid, and it will be the strongest acid in solution that's most likely to do the protonation. This is a reaction between a weak acid and a weak base, so I'm going to draw equilibrium arrows here. The products of this reaction will be our initial molecule, but now we've made an additional bond to hydrogen, so now it's H2, and it has a formal positive charge because the oxygen has shared electrons to make the new bond with hydrogen. At the same time, we also have our HOCH3, and this was from when from the bond breaking from the acid catalyst when it transferred the hydrogen away. Now, the second step is going to be when our substitution mechanism actually starts. So the first step in an SN1 mechanism is always that the leaving group leaves. So here the electrons from the bond end up with the leaving group as it leaves. And so the intermediate will be our carbocation intermediate. Notice that I'm drawing everything in the plane of the page at this carbon because it is sp2 hybridized. sp2 hybridized, which means that it will be trigonal planar in geometry. We also have our H2O, which has left as our leaving group. In the second step of the substitution portion of this mechanism, we add our nucleophile in. So I'm just going to add the nucleophile in right here, the HOCH3, which was in our initial reactants above the arrow. And I'm going to draw it here because this is the step where it becomes involved. So here I'm going to show that the lone pair of electrons on oxygen of the nucleophile is shared with the positively charged carbon, so that we're making a new bond between the electrophile and nucleophile. Now, this carbon that we're adding to is not going to end up being an asymmetric carbon, so it does not matter whether we add from the top or the bottom. So it's not a stereocenter here. So I am just going to draw the one product because it doesn't matter whether I've drawn this as a wedge or a dash. They'd be the same thing. So I'm drawing it as a dash, but a wedge would be equally correct. Okay, so this oxygen, since it's shared its electron to make the new bond, will have a formal positive charge, and we can't have a formal positive charge normally in our final main organic product. So I'm going to use the nucleophile again, since there's excess of it in the solution. It will also be used as the solvent here. I can use the excess to do the deprotonation. So I'm essentially using it as a base here in a final acid-base step. Now, because this is a reaction between a weak acid and a weak base, it will reach an equilibrium here. So I'm going to be drawing the product with equilibrium arrows. And so here I have my wedge to methanol and my dash to OCH3. It would be okay to draw the OCH3 either as a wedge or a dash, but you shouldn't draw the two different products because they're the same here. You should demonstrate that you know they're the same thing by just drawing the one product. That would be the complete acid catalyzed SN1 mechanism here. So just to label our steps, we have number 1 here is the protonation step. The purpose of this step is to turn the OH group into a better leaving group, the OH2+, so that it leaves as neutral H2O, which is a much weaker base than if it had left as OH-. The second step, number 2 here, is that the leaving group leaves. And that is always the first step in a standard SN1 mechanism. And then number 3 here is the second part of our SN1 mechanism, which is that the nucleophile adds in. And then finally, because we used a neutral nucleophile, we ended up with a positively charged intermediate. And so we had to do a final deprotonation step. And the purpose of this step is to give a neutral final product. If I wanted to balance the reaction here, I could also write out that we were remaking our acid catalyst, which is our HO2 with a plus and CH3. So that's the exact same thing as was written under the arrow here to show that it is a true catalyst. It's used in the first step and it's reproduced in the fourth step of the reaction.